Here's 7-2 day 1. Same focus as 7-1, except it's a new technique. 7-1 was all about substitution. 7-2 will be about elimination. The second day you'll see I come back to substitution, because really once you see both of these techniques, what I'm expecting is you can kind of use your judgment as to which is the more appropriate technique to use, and you're always free to use whichever one you want. But there are cases where one makes a little more sense over the other. So the second day of 7-2, you'll see I'll get into a few where I kind of revert back to substitution, because it may actually be the better route to go, but we'll see that later. Today is all elimination, and the ones I'm going to give you, it's the appropriate technique to use. Okay? So with substitution, okay, that goes back to 7-1, you have to have one of the variables solved in one of the two equations. Okay, so here we'd have a little work to do, and we'd run into some fractions if we did it. What I want you to notice here is how the x's and the y's and the constants all line up. Neither equation has been solved, okay, but that's okay, because all like their respective parts are aligned, and let's add the two together. Now you're going to see in the other examples, occasionally I'll have a little work to do to get them ready to add. This is like ideal. I have one of the variables that differ only by sign. Okay, that's something that I need to get if I don't have it, but here I just add them up, and 3x plus 5x gives me 8x. 2 plus -2 is 0, and the y variable is eliminated. Okay, hence the name elimination. And then 4 plus 8 is 12. Okay, notice it has the same effect as substitution, that we've done something to the two equations, and the end result is we now have a single equation with a single variable. Okay, and this is good. That's going to help tremendously to solve. Divide both sides by 8, and we have our x value. Okay? And once we have one of those solutions, I'm going to head right back up to here. You can go back up to either equation. This part is effectively the same as substitution. Now once you got one of them, go back to whatever previous equation you want. I now know that x is 3/2. And we're left to solve for y, but we can do that because it's the only thing that's missing. Kind of looking ahead to the next step, at this point I'm going to write 4 as 8/2. Then I can subtract each side by 9/2, which would give me -1/2. Divide that by 2, and you would get that y is -1/4. Okay? You haven't seen me really do it at all, but if I wanted to go back and check my solutions, I would technically go back to both equations, right? If I go back to my first one and I plugged in 3/2 for x and -1/4 for y, and then simplify that left side, I'll get 4. Okay? Same with the second one. If I plug my two solutions in and simplify, I'll get 8. If I checked and that didn't happen, there's a sign that something has gone wrong and we've made a mistake. All right, example 2, okay. Notice the setup. It still kind of looks and feels like elimination, okay. Typically speaking, if I have work that I need to do to solve one of the equations for a variable, which has to be done for substitution, I typically won't do it, and elimination might be the better. I could take the second equation, I could solve it for y, and then plug that in, okay? Now here is one of the really common things you're going to have to watch out for, okay? if you were to add the two equations, you would notice right away that they're not, a variable's not going to be eliminated. Okay? That problem will be solved if I multiply the second equation by 3. I'll leave my first equation alone and just say 2x minus 3y equals negative 7. But now, after I multiply by 3, I'll have 9x plus 3y equals negative 15. So that first one that we saw where we didn't have to do any multiplying at all, that's not all that common. That was like perfectly set up to just add the equations and do elimination. This is more common that you got to multiply one or the other, or as we'll see in the next example, maybe both, to get a variable eliminated. Now when I add them, I get 11x equals negative 22, or that x is negative 2. Oh, I'll kind of take my pick here. I think I will go back to this one. And really, you have 3 options. You could go back to either the original 2 equations, and if you wanted this one that's been multiplied by 3, you could go back there too. Okay, I usually look for the simplest equation to go back to, and that's why I picked this one. X is negative 2. I'm looking to get y. Negative 6 plus y is negative 5. If I add 6 to both sides, I'll get that y is 1. So that was multiplying one of the 2 equations. Here is multiplying both. Okay, here's multiplying both. Notice you could kind of treat it with trial and error. You probably will look at it and it's obvious that I can't just add them. Okay, but then you look at multiplying one of the equations and you'll arrive at what number would you multiply by. If you want to dive into fractions, you can certainly just multiply 1. Let's say you don't and you want to keep all the coefficients as whole numbers. Here's what you would do. I like that the y's have opposite signs. Okay? So I'm going to take the top one and multiply by 4. I'm going to take the bottom one and multiply by 3. And I want to show you what happens. Okay? I have to do this to all 3 parts, so the top one will have 20x plus 12y equals 36. And then the second one will be 6x minus 12y equals 42. Okay? Notice what happened with the y's. They're all set up very nicely now to be eliminated, and I'll have 26x, no y variable, as we get a coefficient of 0, and that equals 78. Okay? That's a really, really common trick that you can use, is to just, if you have one variable that's opposite in sign, go with the coefficient of the other equation, which is why I did the top equation times 4 and the bottom times 3. Divide both sides by 26. X is 3. Oh, let's go back, and again, if you want to, test it, you could certainly say, no, I'm going to go to the second one, and it's not a bad idea. I'm going to go back to the first, but if you go back and plug in 3 to the second one, we really should get the same thing. So I need to solve 5 times 3 plus 3 times y equals 9. Which would give me that. let's see, I would subtract 15 from both sides and get that. Looking at this point like y is negative 2. Okay, this is a problem in class I'll probably come back to later. But I want to dive into these other two cases that could happen because I haven't really done that yet. And I haven't, in the substitution lesson I kind of talked about some of the graphing stuff that's going on. Keep in mind the same things are happening here. These first three examples that I did, I was solving a system of two lines. Okay, so as far as the case that we were looking at, it was this one. Right, this problem is asking you to work with those equations to figure out which one has a single solution, which one has no solutions, and then this goofy case, which one has infinite solutions. Okay, these other two have infinite and no solutions. If you're using elimination, I haven't shown you yet kind of what that looks like when it comes up, because all three examples have been case 3 where we've had one single point where the two lines intersect. And I don't, I'm sure as you do the algebra you would be fine and you'll get to this point, but then something kind of different happens, and my concern is I want to make sure that you know, when you see it, you know which of these other two cases that is. Okay, so this one's already labeled and tells you right off the bat, this is your no solution case. Okay, so I'm going to tell you right off the bat, I don't even know if these lines have positive slopes or whatever. I'm not going to find out. But just in general, it's a case where that is what's happening. These two lines are parallel, and they're never going to intersect, so we shouldn't get a number point for, where they intersect. Okay, it is the case where the top equation needs to be multiplied by 2. So we'll have 2x minus 4y equals 6. And then the bottom equation is good because the x's are set up to cancel perfectly. Now thinking back to those first three examples, this is just kind of a side note, I think I set them up to cancel, I want to say I canceled y every time. Don't read into that at all, that's not a thing. If the numbers work out where it makes more sense to eliminate x, then do it. So check out what happens here. X's get eliminated, so do the y's. So I have 0 on the left side, but the right side adds up to 7. Okay? Now, that's not true. 0 doesn't equal 7. So if you get both variables eliminated and it reduces down to an equation that's not true. Again, my worry is you kind of do all the algebra and then you get to that point and you're like, what's going on? What happened? That's the no solution case. And I would expect if you get there, I expect that you would know that's what's happening. That leads to that you would know how to kind of interpret that weird result. I shouldn't call it a weird result. It's just a less common. Okay. All right. We haven't seen this come up before. No, I'm looking at my y variables, and they're the same sign, which I don't really like. So I'm going to take the top equation, I'm going to multiply by negative 2. Okay, that will give me negative 4x plus 2y equals negative 2. That got those y values to be the opposite the opposite sign, which I like. So that can come up. And I'm glad we saw that in this example, that the number that you multiply by to get the elimination to work well, that can be a negative number. All right? So look what happens here. Again, the double elimination. X's and Y's both. Look what happens on the right. Okay, before it added up to 7, and we got this, the other one we got 0, equals 7, which was not true. This reduces down to a really simple little equation, but it's true. 0 equals 0. Okay, so now at this point, we're not going to go find any of the solutions, I should say, because there's an infinite number. Okay, here's what's going on. Let's say, I have no idea if that's the correct line or anything close, but let's just say it is. All right. The second line, even though the numbers look different, if you were to simplify them, you would see it's the same line. We actually kind of got the same linear equation in disguise. So they kind of look different. So basically, if you just picked any point on that line, it would be a solution to both of them because it's the same line. Okay? That's why there's an infinite number of solutions, is you could, a line always has an infinite number of solutions. You can go pick any point, plug it into both of them, and it's going to work.